Hi, I'm Ryo Nakamura, a research associate at the University of Tokyo. I will introduce our study of fast latency measurement with BGP Egress peer engineering by segment routing. The Internet relies on BGP. BGP routers choose best paths to destinations by the best path selection algorithm. But it is well known that BGP best paths are not always best when it comes to performance, such as bandwidth or latency. The best path selection algorithm does not care about such performance metrics. Instead, BGP uses AS path length and several attributes, such as local preference. So many studies have tackled this issue, the performance obliviousness of BGP. Google uses SDN, Facebook also implements a dedicated routing mechanism, and RISP and FIFO-based approaches have been proposed. However, the effectiveness of such egress traffic engineering is still controversial, as presented in the Hotnets paper. To begin with, clarifying the effectiveness of egress traffic engineering is difficult because it requires deploying egress traffic engineering, even though it is still hard. We provide a new case study to this argument. We deployed egress traffic engineering on an AS and measured latency to the Internet via all possible paths, including non-best paths. And from the data, we revealed the potential latency benefit of egress traffic engineering. To implement egress traffic engineering, we use the segment routing and BGP egress peer engineering, called BGP PE. Unlike other methods, BGP PE is standardized and implemented in commercial routers. Segment routing, or SR, is a source routing architecture. SR represents any topological entities as segments and steers packets by the segments embedded in the packets. BGP PE is one of the use cases of SR. An ASBR assigns segments to eBGP peers, and the ASBR transmits a packet to the peer corresponding to the segment embedded in the packet. So, SR-based BGP PE enables sending a given packet to a chosen exit without impacting other traffic by relying on encapsulation. We conducted our measurement experiment with SR-based BGP PE at a network where SR was deployed. The network is Interrupt Tokyo ShowNet. Interrupt Tokyo is an annual exhibition of network technologies in Japan, and ShowNet is a large demonstration network built at Interrupt Tokyo. In 2021, the ShowNet backbone network was composed of SR-MPLS and SR-V6 Layer 3 VPN, so we put our experiment on the ShowNet network. The measurement procedure is simple. We performed ping and transroute using Scamper to about 2.6 million IPv4 addresses via 101 eBGP peers. These eBGP sessions are spread over 3 transit providers and 43 peer Ases who agreed to join the experiment. During the 5 days measurement period at the exhibition, we obtained up to 35 RTTs to a destination per eBGP peer. From the data obtained at the experiment, we revealed 3 points: how best are the best paths, peering versus transit, and behavior of peering ASs when they receive packets to not advertise the prefixes. It means detouring. I will introduce these 2 points from them in this presentation. First, we will reveal the room for latency improvement by egress traffic engineering. We compared RTTs via BGP best paths and the minimum RTTs among all received paths for each probed prefix. This graph shows RTT via best paths minus RTTs via the shortest RTT paths for each prefix. 23% of the prefixes have no differences, which means the best paths have the shortest RTTs. Conversely, 77% of the prefixes have alternate paths of shorter latency than their best paths. 44% of the prefixes got up to 10 millisec latency improvement, and 18% of the prefixes have alternate paths of 10 to 20 millisec shorter latency than their best paths. The result where 77% of the prefixes have alternate paths of shorter latency is surprising, and we found that the reason is the imbalance of egress Ases. 88% of the BGP best passes were directed to a transit provider, transit A in this graph, but the other two transit providers occupied 81% of the shortest RTT alternate passes. This imbalance of egress Ases on the best passes arose from the deployment process of ShowNet. ShowNet established the eBGP session with transit A before the others, so the other BGP attributes being equivalent, the older routes were chosen as best routes. This case also demonstrates the performance of rebelliousness of BGP and the potential benefit of egress traffic engineering. Next, our measurement sent ping and trace route to 2.6 million IPv4 addresses via transit and peering Ases under an agreement. From the data, we can reveal the behavior of the peering Ases when they receive packets distinct to prefixes that the peering Ases do not advertise. From the trace route data, we found 91% of the peer Ases do not block packets to non-advertised prefixes. This result raises a security issue. Lack of data plane filtering can lead to malicious detouring over peering links. Let me conclude the presentation. We provide the fast latency measurement with SR-based BGP PE as a case study of egress traffic engineering. Also, the degree of improvement depends on the performance of rebelliousness of BGP at the measurement point. Egress traffic engineering can improve latency. In addition, we demonstrated that SR-based BGP PE has the potential for practical measurement of external connectivity, such as peering versus transit and detouring. We believe that a stable network where SR and BGP PE were deployed would bring an opportunity for a more comprehensive measurement of the long-standing issue of BGP. Thank you.